Okay, so that's where we would start, okay? These are the formulas for finding these center properties. Center of area, which is a centroid, center of volume, center of mass, and center of gravity, which is a weight centroid. Okay. All right, so what we just did is we added up a number of, in this case, x bar distances, which were our moment arms times weight, divided by the total weight. Now, if instead of a series of discrete weights, let's say we had a distribution of weights, something like that, well, what we would have had to have done was to break up that distribution into a bunch of little weights, right, like that. And then we would have found the distance to the centroid of each of those weights coming over in the x direction. And of course, we would have broken those weights up into smaller and smaller weights and found more and more of them. And of course,
to just cut it into a rectangle or triangle and use that half of 1/3.
It depends on how refined an answer you want. If this is a curve here, you know, you wouldn't get a perfect answer, you know. So y'all know where I'm going with this, right? As we do this and break it up into more and more pieces, we have to sum those things up faster and faster because there's so many of them, and that takes that sign and accelerates it to the right, and then it deforms into something like that, right? Okay, yes.
We're doing the area under the curve for the triangle, the 1/2 base times height. That's technically like the interval, right?
If you break those triangles up small enough, right? You know, that's what you're doing.
Like the slope is like you can think of the slope as like the hypotenuse of the triangle.
Yeah, or the tangent to the curve too. Yeah, right. Yeah, right. You could do that. And you know, you probably have done that. Simpsons, I don't know, there's all those different rules, and I can't remember what those things are, but for approximating areas under curves and things. Okay. So yeah, you could do that. Okay. All right, so there's different approaches on these. Why don't we start off with an algebraic one though, because we don't always, you know, in industry, we don't always have these nice functional curve relationships like we do in textbooks. So let's just start with some algebraic ones. And we do that. And this one is on, I don't have this one. This is, you'd have to just draw this one up. So let's see if we can find the centroid of a shape like that. Okay. So just a rectangle with another piece on it. Let's just find x bar, or let's find x bar and y bar, okay? So what we're going to do with this to find x bar is we're going to add up the little x bars to the centroids of areas, multiply that by the area itself, and then divide it by the total area of the shape, which I'll designate with a capital A. All right. So the thing on this to do then would be to break this thing up into smaller pieces. Maybe put a rectangle up top there and get the area of that. It's 4, which is 2 by 2. And then, you know, I like to make these as visual as I can, so I'll put centroid marks on there. And then, let's see. This other one is 8 by 4, right? So this area is 32, which is 8 times 4. And then I'll go ahead and draw in these arrows to show the distance to these centroids. Half of 8 is 4. And then I've got 6 plus 2 over 2, which is 7. So what I'm doing there, I'm going 6 plus 2 over 2 is 7, and 8 over 2 is 4. And then I'll multiply them out. So what do I got here? I've got 4 centimeters squared times 7 centimeters plus 32 centimeters squared times 4 centimeters. And then I'll divide that by the total area, which would be 32 plus 4. And that's square centimeters. Okay. All right, so what do we got there? 28 and 128? Is that 156? Let's enter. Clear on this. So 28 and 128, 156. Divide by 36. 4.33, is that about right? All right, and then how about Y bar? What do we got? We've got half of 4, so that'll be 2, and that equals 4 over 2. And we got this one, that's going to be 4, that'll be 5, won't it? Which is 4 plus 2 over 2. So Y bar will be the sum of little y bar times the area over the total area. So what do we got? We've got 4 centimeters squared times 5 centimeters plus 32 centimeters squared times 2. And then we'll divide that by 32 plus 4 again. There we go. So what is that? 20 plus 64, right? And then we'll divide that by 36. We get 2.33 centimeters. Everybody okay with that?
And the Y bar is the distance to the center of gravity? Is that what this is?
Yes, yeah. So what we got here when we go through this is we just figured out that the center of gravity is right here. So it's 4.33 coming over that way and 2.33 coming up. And being as if we assume that's a plate of uniform density, if we measure those distances on the plate and then we tip the plate over and put it on a point, it'll balance at that point. So that's the centroid of the plate. Okay? And that's the idea. Okay. And if you had a curved kind of surface there and you wanted to find the centroid, you could do it like that, right? You just balance it on different edges there and intersect all the balance lines, and they'd intersect at the centroid. That'd be a way to find the centroid too if you had a shape that was kind of complicated and hard to work with. Okay, so those are all balance lines, you know. So I can balance this thing on these lines. And then if I intersect them all right there, I can balance the thing on that point. Okay. So that's kind of how you find a centroid. Oh, okay, so to do that, I found the areas, found the distances from the two axes, x and y axes, to the centroid. Notice that I consistently measure from the same set of axes, the x and y. So I have to add in those offsets. You know, on this one I had a 6 centimeter offset to get to that point, plus one more. On this one I had a 4 centimeter offset plus one more. Okay, so you always have to start at the same axes as you do this process. Okay. And then I just ran the numbers. Okay, x bar a over a and y bar a over a. Okay. All right, now let's look at a more complicated shape. And let's get more systematic about this. 630, okay? Because I think when we do the final exam, you're going to want to get more systematic about this. So we might want to get a table going here so we can just kind of walk on through this, okay? Okay, step by step. All right, so what I've got there is a rectangle. Looks like we slapped a couple triangles on there. Plus we have a semicircle cut out and a skew in there. And let's see what we could do with this. Okay, so we want to find the centroid of that shape. Notice we already have an axis system in there. So we want to reference the centroid to that axis, right? Those axes, I guess I should say, with the origin located where they intersect. So everything will be measured from those axes. Okay. All right, so what I'm going to do is I'm going to call them names, and I'll just number them, Roman numerals 1, 2, 3, and 4. And then I sketch in the distances from the axes to the centroids of each of the shapes. So I've got triangle 1, that's semicircular cutout 2, the big rectangle 3, and the small triangle on the right, which is 4. Okay. So that's what I'm going to start with. And, I go ahead and sketch those little arrows in, because that way if I'm getting an answer that looks a little goofy, I can see it. Those I can tell by the length of those arrows about what the numbers should be. So that'll help me, to avoid making a blunder on one of the calculations, because I'm looking right at it, okay? Now, this is a collection of triangles and rectangles. The one thing that I would add to this is a circle. And actually, we'll use a quarter circle when we do that. Now, the centroidal distances for a quarter circle are 4 pi over 3r. Okay? That's how you get from the two edges of a quarter circle to the centroid. So keep in mind that if you put two quarter circles together, you get a half circle. You'll have those two centroids mirror images of each other. So the centroid of a half circle then is based on those quarter circle measurements. It's right there. Okay. Okay. So the distance from the long straight line on the half circle to the centroid, that would be 4 pi over 3r. But this distance here, if you're measuring from the side over, that's just the radius is all it is. Okay, there's nothing fancy about that other measurement.
Won't the R have to be on top?
I think it does. Yeah, I think I've busted that. I'm checking on that right at the moment.
Because otherwise, someone increasing that round.
Yeah, the units.
Probably mean it's gonna be closer to the.
Yeah, the units aren't working out either, but let me just, I think I busted that. Let's have a look. I think it's 4 over 3 pi. Yeah, sure enough. Okay, so that's my bad. 4r over 3 pi. Thanks. There we go. All right. All right, so off we go. So I get a nice little table set up. So I got the 4 parts there for the column on the left, and then I've got the total area. That's the next column, X bar, then Y bar, and then I just multiply the stuff out in the last 2 columns. And then I do the final calculation on the bottom. All right, so let's go through one of these. Let's do that triangle on the left. So that thing is 12 by 24. So I'm doing part number 1 here. It's 12 wide by 24 high. So I'm doing this right here. Okay, so 1/2 12 by 24 is 144. I just put the units up here in the table. That way I don't have to write them down all the time. So it's centimeters squared. All right, now I'm coming from the y-axis and I'm going over in the x direction to the centroid of that thing. That thing's got a base of 12. 1/3 of 12 is 4. That's to the left, so it's -4. Now, there's a lot of ways to calculate y bar. What I'm doing there, see, I've got 12 and 12, so that total height is 24. So what I've got here is I'm going to basically, to get to that centroid, the way I'm going to think about that is I'm going to go up 12, and then I'm going to come back 1/3 of 12, or excuse me, 1/3 of 24. So that's what I'm doing there. So I'm going up 12, which is this number. That gets me to the base of the triangle. Then I got to come back 1/3 of the height, which is 1/3 of 24. And the result of that is I go 4 above the x-axis to get to that centroid of the triangle. 12 up, 1/3 of 24 back down, because the centroid for a triangle is at the 3rd point. Okay. So that's all the kind of calcs I really have to think through off the diagram. I got the area, x bar, and y bar. And then I just multiply after that. So to get the y bar, I'll take the 144 times the 4, and I'll get 576. And then to get x bar, I'll take the 144 times -4, and watch your signs on this stuff, and I'll get -576. Okay. Now that's for that entire triangle on the left, even though part of it is cut out by that semicircle. I'll handle the semicircles separately. Okay. Doing all right on that? Okay. Okay, the semicircle, it's half of a circle, so minus 1/2 times pi r squared is about negative 127. Now that's a negative area because that semicircle's a cutout. You've got the diameter of it called out here. It's 18. Okay, now you're given the dimension to the center of it from the y-axis. It's 6. Okay, that's just given on that dimension. And then we'll figure out the the y bar distance. It's kind of like the one we did before. We're going to have to go up 12 and come back the 4r over 3 pi. So we're going up 12, but we're coming back 4r over 3 pi. So that ends up equaling 8.18. So then we just take the area times the y bar to get y bar A, and we do the same thing for the x bar. Okay. Okay. So what we're doing, we're filling in that far right column, those two far right columns. Those are what we want. We also want the areas because that's what we use when we end up calculating the centroid. Okay. Why don't you do the line there next for the next two parts, the rectangle and the triangle. So the rectangle's number 3, so start with that. That one should be pretty quick. So just get the area of the rectangle and then the x bar and y bar distances. So just area and then x bar and y bar. And then we'll climb out. Okay, so the area of that rectangle is 1152. And X bar is half of the 48, it's 24. And the Y bar is 0. Okay. Now we can handle these pieces separately, you just got to figure out how to break them up. The fact that that semicircle overlaps the rectangle and the triangle doesn't make any difference. You just subtract it out, find its proper distances and area and go through and subtract everything out because it's a cutout. And we got the rectangle, then the triangle. Same drill on the triangle, just find the area, find the offset distances. That's about it. So you do want to be watching your signs on these, okay? So the area of that triangle is 108, X bar is 54, Y bar is -8, because it's below the X-axis. Okay. And that -8 carries through for the Y bar A, it's -864. And the X bar A is 5832. Okay. You got any questions on that? So that's what you want to fill in, once the first 3 columns you fill in off the sketch, then you multiply the area times the offset distances, X bar and Y bar, to fill in the 2 right-hand columns, okay? And then we just add up the appropriate columns, the area and the X bar A and the Y bar A. You don't need to add up the 2 columns in the middle. They don't really mean anything to add them up. And then you just divide out. Take the X bar A over the total area. You get the X bar, it's 25.2. Y bar A over the total area gets you -1.04. And that's where the centroid's at. That's where the balance point is at for that shape. And we use that centroid for a number of different things. In dynamics, we use a center of mass. And that's the point about which an object will rotate if it's traveling freely through space. And then if we in strength of materials, we use the centroid to calculate beam stresses. Okay. So as a last check, what I like to do on these is just have a look at, just plot up that centroidal location and be sure that it makes sense, where I've got it. So I'd measure about 25 over, as near as I could figure, and plot that and measure down about 1 centimeter from the x-axis. And put a point there and just look at it and ask myself, is that reasonable? Is that a balance point for that object? And this one, works out pretty well. We're at 25.2, and then we come down. I don't know what color I got going on here. So that'd be down about there, I guess. Okay, this seems reasonable. Seems like a reasonable balance point right there. Okay. All right, so that's the centroid. All right, we're good. You got any questions on that? All right. Maybe get you a couple of these for Wednesday. How about 341 and 2?